Okay, so the goal of these sessions again was to sort of for you guys to do the tutorials on your own, and then we would have sort of an interactive kind of question and answer session, maybe go through some of the details of the tutorial each week until we sort of get through all of the tutorials. So we're going to start with a single particle tutorial this week. And if we don't get through all of that, we'll continue that next week or switch to the other one. We'll just sort of see how things go. And then we'll do the subtomogram averaging tutorial after that. And then we'll do the dynamics flexibility with the Gaussian mixture model stuff tutorial last. And that last tutorial actually only sort of exists so far. So I guess I'll probably need to write the new version of it before then. Let's see, let me share my screen. Right, so the plan is we're going to go through this tutorial. It's still labeled as the EMAN 2.3 tutorial at the top, which is interesting, but that's probably fine. Hang on, let me just check and make sure I've got the current version open here. Is that what other people had?
Yes.
That's what I have too.
If you want, Steve, I could try and make edits while you comment on things. Like if you want me to change 2.3 to 2.4 or whatever. Well,
I have no objections if you want to. Well, you can't make edits to that. That's not this tutorial is a PDF. It's not.
I see. Okay,
Yeah.
I just a thought.
Yeah, no, I understand. I appreciate the thought. And when we do the subtomogram averaging tutorial, then that's actually in the wiki, so that would probably work. Yeah, I'm just looking because I'd swear I've updated this tutorial since that time. Weird. All right. Well, anyway, I'm sure it's fine. This tutorial has been pretty stable for a lot of years. So let's see, share again. Oh, someone chatted something. Yes. Okay. Fine. Hopefully everyone who's interested in participating in this has actually gone through the tutorial on their own machine, or at least gotten as far as they can. Mia, one of my the rotation students this term, pointed out that when she got to one particular step, which we'll probably see later, there was a bug and she couldn't do a particular thing. There are ways of getting around that particular problem, but that will also depend on which version of EMAN you had. It was sort of a recently introduced bug, which was also recently fixed. So if you happen to have a version of a snapshot version of EMAN from the time when that bug existed, then you might have run into it. But it's a fairly minor bug. It's just irritating that it has an impact on the tutorial. Usually when I go through these sorts of tutorials, I go through the whole thing myself and test everything out before we start the tutorial process. But this week and last week have just been so utterly busy for me that I haven't had time to do that this time. So we will find out together if we run into any problems. So introduction to tutorial. So my thought is that I will just sort of go through some of these steps myself on my local machine here. And then I will periodically sort of ask people, if you have any questions, you can just unmute yourself and ask your question. You can send it by chat, but I don't guarantee I'll notice all of the chats. And I will periodically sort of ask people, if you got the same sort of thing. And I thought maybe we would actually go through some slight variations on the tutorial, like actually boxing out the particles ourselves and that sort of thing, which is sort of explicitly avoided in the tutorial. So you should have all downloaded this workshop data set. I have it here. I got this folder called bgal, which I unzipped from the archive file. And if we look in the bgal folder, we'll see that it has an info folder, original boxes folder, and original micrographs folder. And if we look in the info folder, you'll see the only file in there is this project.json file. One of the very common problems we have when people try to go through the tutorial is when they get to the initial step here, this project manager step, they don't read very carefully and they don't do this, which is basically setting the basic project settings, saying, you know, what the voltage of the microscope is, what the angstrom per pixel value is, and that sort of thing. So people historically very frequently missed that step, which then led to them having to go back to the beginning of the tutorial and start over again when we were a couple of hours in. So to avoid that problem, we now distribute this already set project.json file along with the data. So if we run E2 project manager, so I'm going to be doing this kind of fast because you should have already done it yourselves. So you should be familiar with everything I'm doing. So the goal is not that, oh, you're going to learn what I'm doing following along. The goal is hopefully that you've already done this and you're just kind of seeing what I do and then identifying any places where things happen differently. So if we open this and we then go to project, now on Macs, this is an interesting little glitch on Macs. This has nothing to do with EMAN. It's related to the Qt GUI system that we use. When you open, sorry, just having some button clicking issues. Where is it? Yeah, when you first open a GUI window like this, the menu bar won't work correctly. So you click on the menu bar, nothing will happen. But if you click away to another window and then click back, then it'll suddenly start working. It's been a problem that's part of the Qt system for many years now, and they just never fixed it. Anyway, if we edit project, you should see all the settings here are exactly what it tells you to fill in the tutorial itself. So we don't actually have to do anything here. All right, so our first step is to import data into the project. So the data comes in this original micrographs folder instead of a micrographs folder. This is just sort of to emulate what you might get if you're collecting data yourself. So you collect data yourself, you'll have, typically you'll have like a big movie stack, and then you'll use Motion Core or some other tool that you prefer to align your movies and then produce a bunch of aligned micrographs. And that's sort of the step that we're starting at in this process here. Import micrographs and estimate to focus. Now, last week, I showed you this evaluate and import micrographs tool where we kind of looked at the power spectra of some of the micrographs and looked at what some good features and bad features are. So we're just going to use the built-in automatic tool here this time. So we need to pick all the micrographs that we wanted to import. So we'll go to the micrographs folder and select all, say OK. And basically all those file names are now in this little text box here. The options here should all be basically correct. I'm going to set my number of threads to 8. I'm running on a one of the new M2, not M2, but Media Max. What are they called? Anyway, I'm running on one of the newer Macs, and it's got several cores in it we can use. So I'm going to change threads to 8. These should all be correct. We need to uncheck invert because the data has already been inverted. The data is old enough that the X-ray pixel filter is something we do want to include. For a lot of modern data collected on counting mode detectors, this isn't strictly necessary. Although generally won't do any harm either. And that's basically it. So then we'll say launch. And we can look at the main terminal window here. It's always a good idea to have that terminal window somewhere where you can at least sort of see what's going on, because that's where a lot of sort of progress output will appear. You can also open up this task manager window, and that'll allow you to sort of monitor what's going on more or less.
I had a question at this point.
Yep.
Why do you invert the images? Because
I did not invert the images.
No, just in principle, like when importing images to EMAN2, why do they have to be inverted?
So
At all.
there are two conventions for image contrast. The higher electron density could be darker in the image, or higher electron density could be lighter in the image. There is an asymmetry in the image processing, meaning that some of the algorithms care whether things are darker or lighter. So every single particle reconstruction package picks some convention for that. The EMAN convention for single particle analysis is that brighter things in the image should be higher electron density things. So if the raw images you get are darker rather than brighter and high electron dense regions, then you need to invert them. And that just means multiply by -1. Does that answer it well enough?
Yes, I was just wondering because I'm used to darker particles in the whiter background, but I understand. Yes.
Yeah, so it's a convention, and it's actually the convention that's used by pretty much all the single particle packages nowadays. So when you see the raw micrographs originally, they will look darker nowadays. Now that wasn't actually always the case. When you collected data on film, there was often a conversion from what you see on the film to optical density, which anyway, old stuff from history. Anyway, there are historical reasons for all of these things. Okay, so this process finished. So now if we open a browser here, we'll see that we have a folder called micrographs now, which contains the imported version of the micrographs. Now in this case, it didn't really do much of anything to the micrographs themselves, but it did make a measurement of the defocus and other CTF parameters for each micrograph. So if you look here now, you can see now the info folder contains a file for each individual micrograph or frame that we imported in these JSON files. If you want to see any of that information, you can single click on that file and you can open the browser here, and then you can see the stuff that's in each of the files. You can see the CTF frame parameters, EMAN2 CTF. So here we can see the defocus and the other parameters for the image. That's not something you really need to do here. I'm just pointing out that it exists as an option. So we now have our micrographs folder, and then the next thing we need to do is find the particles in our micrographs. So if we look at the tutorial at this step, so we've just done evaluate images and import data. Right, so we skipped, we did this, the import only step. We did not do the evaluate and import step. That's what we talked about last time. And where we had images like this where we were looking at the power spectrum. Okay, the next thing is extracting boxing particles from the micrographs. Now, in this particular case, for the tutorial, we provide this original boxes folder, which contains the particle locations already selected for all of the micrographs in this project. Maybe all except one. I'm not sure if one was left out or not. But anyway, for all of the micrographs that we're going to do anything with it in the project. These boxes, or the original boxes that were selected when this data set was first published. So this is a data set that was published by Sriram Subramaniam's group as basically sort of a microscope test. So beta galactosidase was one of the sort of 2010 plus one of the earlier tests for microscope quality and image quality and doing single particle analysis and that sort of thing. So anyway, when this was published, this is a subset of the data that we're working with here. The full data set was able to achieve pretty high resolution, but it consisted of a much larger data set than we're working with here. So this is all of the box locations for the subset of the data that we have. So the approach the tutorial takes is to just use those box locations, and we use the import box files to read them in. But I thought we might actually go through the deep learning particle picker really quickly today and learn how to go about picking particles, because that's something, we have a tutorial for it, but it's something that people often have a hard time learning how to use properly. So to do that, we're going to launch the interactive particle picker. And the box size that we're going to use is going to be the same as the box size. It can be changed later. It's not a big deal, but it's the same as the box size that it tells you to use in the tutorial. So here, when we extract boxes, it tells you to use a box size of 256. The particle size doesn't actually matter for these purposes. The only thing it really does is when it draws each box on the screen, it's going to draw a square box, which is the box size, and then it's going to draw a circle in size, which is whatever the particle size is. So it helps sort of measure how big things are and that sort of thing. So we'll just put a number in here, but it's not actually important for anything. Then we're going to say all micrographs. So it's going to open all of the micrographs in the project. And we're going to say 8 threads again. And I'm going to say GPU for the device. So there actually is beginning to be some support for TensorFlow for the new Mac M1 and M2 CPU, GPU processor combinations. So you can actually say GPU now and get some benefit out, at least out on these new Mac computers. Anyway, so since we say all micrographs, we don't actually have to fill anything in this box. If you say all micrographs, that overrides anything you put there anyway. So that's it. We do need to have the GUI button checked. Otherwise, it will be trying to just do background processing for extracting particles after you pick them. Right. So all of the stuff that I'm going to be showing you here, in theory, exists in the deep learning particle picker tutorial on the web page, but we'll go through it interactively so people can ask questions and that sort of thing. Right. So when we open this up, we'll get a couple of different windows open. We get a control panel window up here at the top. And I'll make that a little bit smaller just because I've got my screen set to 1080p here. Ideally, when you're doing this this kind of work, you'd like to have a 4K monitor or something, something big and really high resolution to give you a little more screen real estate to work with. But I've got a 1080p since we're going to record this and put it online. So we'll see a window here with the micrograph. This is just the first micrograph in the set. So we'll zoom out a little bit here so we can just sort of see some of the particles floating around in the background. The particles window, which will contain the boxed out particles once they've been selected. And then there will be a couple more windows that appear as we go through this. So again, we're looking at this first image. You can see it's kind of hard to see the particles, right? If we open just the control panel, if we middle click on this window, open the control panel, there are some things we can do. We can do like histogram Gaussian, and that can help a little bit, or histogram flat, that can help a little bit to see the particles. If you like seeing particles that are dark instead of bright, you can hit the invert button. That's not going to change the data in any way. It's just changing the representation on the screen. So you don't have to worry about it messing up your data or anything here. You can just toggle it on and off. And actually, sometimes the toggling process makes it easier to see things too. However, since we're using the particle picking tool, these features are things that exist for any 2D display in EMAN. But since we're using the particle picking tool, there's this button up here, Filter Display. If we click on that, you'll see it actually does a very nice job of sort of enhancing the contrast and making it a lot easier to see where particles are and what things are and aren't particles in here. You can see there's a bunch of places where there are sort of particle aggregates clumped together and that sort of thing. But then it's easy to see some individual particles floating around there. Now, again, this is just for display. When I select individual particles here, they will actually be the original raw data, not the filtered version that we're looking at here. All right, so there are several different auto boxing tools available in this program. There's a local search by reference, a Gaussian method. What we're going to be talking about now is this neural network picker. So we'll switch to the neural network picker. And to use the neural network picker, the first thing we have to do is we have to train the neural network picker. So we're basically going to create a network which knows how to recognize particles and distinguish particles from background and bad stuff that we don't want to box out. So the way we train it is by giving it examples. So there are 3 types of examples. You can give reference examples of good particles, of things that aren't particles but still have strong contrast, and things that are background, which aren't anything, which are just sort of ice in the background of the image. So we'll start by giving it some good references. So I'm just going to hit good ref, and then I'll click on a particle and I can drag around and try to get it pretty well centered. Now you'll notice the box vanishes as soon as I let go of the mouse, but a new window appeared here where it says box refs, and the particle that I picked appeared down there. Now you'll notice that I don't have there's a little black box in the corner here. This is another issue with the installation on my Mac. Sometimes it happens on Linux too. There will be some issue with the fonts and how they're interacting with the program, and you'll see just black boxes down here. It's a bug that's been around for a long time, but it only happens on some machines sometimes. So we haven't managed to sort out exactly what's going on yet. Anyway, that doesn't matter. The number isn't useful for anything in this case. Anyway, so that's the reference that I picked out, and the goal is to pick something on the order of maybe 30 or 40 things which are particles. Now, when I move around here, you could say, oh, well, that's a particle right there. But you can see that particle surrounded, it's sort of touching and crammed in with a bunch of other particles. If I put that in as a good reference, then it will kind of learn that it should try and box out stuff like that. What we'd prefer to do instead is try and find particles which are fairly isolated from other particles. It's okay if there's, maybe one neighbor nearby or something like that, but we'd rather not have, go in the middle of these big clusters. You'd like to sort of try and find particles which are fairly, monodisperse. So we don't want to do this from just one micrograph. We want to go through several micrographs, which cover a range of different defocuses and that sort of thing, and pick just a few references from each of these. Now, I'm looking at this micrograph, and you see, look, there are particles all over the place. But most of them are, kind of in that situation of maybe touching other things, or maybe being a kind of questionable quality and that sort of thing. So when you're picking these good references, you really want to focus on particles that are definitely good particles and they're kind of isolated from others. So I'm going to go through multiple micrographs to find particles which I sort of really like. Now you do want to get a wide range of different orientations. So you want to get particles which are in every sort of conceivable orientation that the particle might be in. So there's absolutely no reason you need to try and get everything in one frame or anything like that. The goal is to get a diversity from a diverse set of frames. And again, we're going to try and get a total of something in the order of 20 to 40. The exact number you get doesn't really matter all that much. I don't like any of those enough. I might pick something like this, although it's got a little bit of an artifact nearby. I mean, you don't have to be perfect about this either. It's just the better the job you do with this, the more likely it is that you get a good trained network on the first attempt.
What's the significance of the circle within the box? And
the circle is just what I put in as particle size here.
Oh,
so it just allows you to center the particles a little bit better. And it allows you to sort of measure the size. So if you think the particle is a very different size, then that might key you in on the fact that it's not what you thought.
Yeah.
Now, just because I'm not boxing particles that are in close association with other particles doesn't mean they won't get boxed out by the network in the end. In the end, it's going to kind of depend on threshold. It just means that it's going to prefer particles that are monodisperse over particles that are touching other particles. So I've got a pretty decent set here right now.
And just to clarify, it'll for the neural network, it'll train off the entire box size, not just the circle, right?
Yeah, it's training from the whole box. Yes, that's correct.
Okay.
The goal, though, is to get the particle that you've selected in the middle of the box. That's what it's going to be looking for. It's going to be going through the whole micrograph, and it's going to be trying to put a spot in the middle of every particle that it finds. Now, there's some tricky things about this particular specimen. It's kind of long and narrow. And what that means is the end-on view actually looks kind of like ice contamination. So this, where you can actually see that trimer kind of shape in the middle, this actually is like an end-on view of the particle. So it's not ice contamination that we want to get rid of. We actually want to include stuff like that. And this is probably a tilted view a slightly tilted end-on view of the particle. It's, it's sort of just the right size. That's compared to things like ice contamination like this, which have maybe sort of a similar kind of appearance, but they're much different in size. Or this. This is probably not a particle. This is probably a blob of contamination of some sort. It's a little difficult to tell in this particular data set sometimes what's good and what's bad. Okay, so I've got a decent size set now of good references. So let me move to bad references. I don't want to take the whole session on this particle picking thing if we can avoid it. So now for bad references, I want to pick stuff that I want to exclude. So I want to include something like that, maybe. Now you have to be a little careful about this, because if you include too much stuff like the edge of this particle there inside the box for the bad references, then it may actually try to train the network to exclude real particles. So you want to try and mostly box out things which are definitely bad regions and don't include much in the way of real particles. So here's a really nice example of definite ice contamination. Overall, this is actually a really good data set. It has very little ice contamination. The ice thickness is just really nice. It was, like I say, it was collected as sort of an example data set of good data. So for bad references, you want to make sure that you sort of cover all of the different types of things which are bad, which might exist in your data set. But the number doesn't have to be all that large. If you pick, and you might say, oh, is that a particle? Yeah, I don't think so. It's a little bit too high contrast at the edges, and it's a little bit too big. So I don't think it's actually a particle. Or like this, what the heck is that? It's too big to be an individual particle. It could be just a couple particles stuck together, or it could be some sort of funny ice. This is definitely, some sort of ice contamination, something we want to get rid of. All right, so we'll start with just that for the bad references, and we'll see what we get. So now let's do the background. So the background, it's important to include background examples from several different micrographs at different defocuses, and covering sort of different textures, because sometimes if the ice is a little bit thicker, you'll see different texture in the ice in the background a little bit, and you want to make sure that you give it representative examples of different types of that background ice. But you only need to give it 1 or 2 examples for each frame, and you don't have to cover every frame, right? If there's a frame where the particles are so dense you can't find any background, that's fine. It's not a big deal. We just want to give it some examples of what the background looks like. So this process should take, on the order of, maybe 10 or 15 minutes to get the network trained. Okay, so I think that's good enough for now. So I've boxed out a bunch of each type of particle, and the next thing I have to do is hit train, and that's going to train the network. Now, if we go back to the console while it's training, you can see it's using the metal device set to Apple M1 Max. And we'll see this sort of training process as it goes. So it's actually training 2 different networks here. It's training one network to recognize the difference between the background ice in the micrograph and the particles. And then it's training another network to represent the difference between particles and things that aren't particles but have high contrast. In the original version of the picker, we actually only had 2 reference types, things that weren't particles and things that were particles. But we found that it was really difficult to get the network to properly learn everything, because it had to contend with both these really high contrast things not being particles and these really low contrast things not being particles. And it was really hard to get a good network to do everything. So by splitting it up into 2 separate stages, and that's why there are 2 threshold values here back in the particle picker, we actually get much better results in general. So, all right, that's the first one. And if you're using an older version of this program, you may find that it actually only does 20 iterations of each, not 40. I found that it seems to do a little better if we do 40. Another thing to be aware of is if you train the network once and you decide it's not working well enough, and you hit the train button again, it will start off from where it left off. So if 20 wasn't enough, you could always just hit the button again and it would train up to 40, but I changed the default to 40 because it seemed to be necessary for most situations. Almost there. And what you should see is this number will get smaller and smaller and smaller. If it stops changing and just sort of sticks at a particular value, or if you start seeing it doing a lot of oscillating back and forth, that means that it's gotten pretty close to converging to a good network. Okay, so the network is now trained, and now we can test it. And we want to test it just on individual micrographs first. And on the individual micrographs, we'll use that to adjust the threshold settings and decide whether we need to train it better or not. And then when we've got everything set the way we want, then we just say auto box all and it'll run everything. So let's just try it on this particular image and see what we get. Okay, so it's doing an okay job. It's probably grabbing a few things, too many things, a few things more than we'd like. So let me bring the particles window to the front here. And we can kind of zoom out here. And these will be all the particles. Let me just turn off those annoying black boxes. You can see the particles in the original image are pretty hard to see. They're a lot easier to see over here. Anyway, we can look around the image here, and it's doing a decent job. I'm just trying to see if it's picking out too many things which are too low contrast. Like, maybe that's not a particle, and this seems to be something stuck together. So maybe we'll try raising the threshold a little bit and hit auto box again. And you see that'll get rid of just the worst things. And then we can play with that threshold a little bit until we get rid of some of the stuff which we think we probably don't want. Right, now, you don't want to just do this on one image. We'd like to run this auto boxing process on all of the micrographs at once with the same threshold. So we want to test it on a couple of different micrographs. And in particular, we want to make sure we get some micrographs that have some of that contamination. So we want to make sure it doesn't box out things like the edge of the contamination. Okay, now we can see here that it is boxing out a bunch of things in the edge of the contamination. So now we need to play with this threshold and see if we can get rid of that. Now, you have to be a little careful. This second threshold value is very sharp generally. So once you get above a particular threshold value, typically it'll say, oh, I didn't find any boxes at all anymore. And so if I raise this, too high to like, that, no particles found, existing locations unchanged. So it won't get rid of the boxes if it doesn't find anything. It'll just put that message up on the screen. So that's too high a threshold. So let's try that. Oh, too much still. It's a very sharp cutoff, but very sharp cutoff, and you may not be able to achieve what you want. So if we find ourselves in this situation, I actually sort of intentionally did this by not picking very many bad references. You'll find you can't get rid of the stuff you're trying to get rid of with the second threshold. This image also seems to imply that we probably want to raise this threshold even a little bit more. And we can go back and maybe that was too much. Oh, I see. It jumped way the heck up. Oops. Well, we'll lower it down until we're getting most of the particles here. Okay, that's not too bad. It's it's missing some, but missing some is better than putting in a lot of garbage. All right, but we still need to deal with this. So what do we do? Well, what we'll do is we'll go to bad refs, and then I will put a bad reference right on top of the thing that it thought was a particle. And then that will add to the training set. It doesn't replace the training set. We're just adding more things to the training set. It will add to the training set exactly the thing that it thought, oh, well, that was actually a good particle. And then hopefully the next time it trains, it will take care of that problem. So let me take a look and see what happens here. Yeah, once again, it found something there. So I didn't give it enough good bad examples last time. Let's try this one. Well, this isn't too bad. So it's actually finding the particle there. It's included a little edge of this particle, but that's probably acceptable. That might get thrown away at a later part of the processing anyway. Let's try this one. Okay, so it did a good job of avoiding that one. So let's go back to the image where it did a bad job, and just so we can look at it. And I'm going to hit train again. And again, we're going to have to now wait through this 40 iterations. If you're using an NVIDIA processor on a workstation instead of my little Mac Mini, you get a lot more acceleration out of the deep learning process than you get from the M1 Max chip at this early stage. So this will run substantially faster if you've got a Linux workstation. Anyway, we'll let it go. Any questions about this while we're waiting for the next couple of minutes? Okay.
While selecting particles, is it possible to adjust the value for the low pass filter? Just to, I don't know, identify particles easier in the beginning before setting this neural network up.
What low pass filter are you talking about?
I was wondering whether it's possible to implement a low pass filter when looking for particles in general before training your.
Well, this visual display that we're looking at here has been filtered in several specific ways to enhance the visibility of particles, right? You know, if you look at it without, I can't do it while it's running, but as soon as it finishes running, we can do that, right? If you look at this image without that filter, it's almost impossible to see where the particles are clearly in some of these micrographs. The low pass filter won't do anything in particular for the training of the network. It's a convolutional neural network. So if a low pass filter helps it to learn the correct particles, it will build a low pass filter into the network itself automatically. So there's really no point in artificially doing a low pass filter before that. As long as you can recognize the particles well enough by eye to identify them for training the network, you're fine. Almost. Okay. Let's see if we got a better result. Nope, we got a worse result. That's because I'll probably have to play with the threshold again. Nope. Not sure why those threshold values keep changing so much. All right, so I managed to get rid of, you can see that actually is a particle. So it's not grabbing the edge of the box, it's grabbing that particle that's near there. So I'm not sure why it keeps adjusting these slider ranges so much, but yeah, and again, that's a particle associated with that we probably, we probably should get rid of that one, but I'm not sure. You can see we're getting rid of a bunch of other things that are particles too at this threshold. So we could try and train the network again. I don't think I want to take the time to do it today. I probably would train the network a little bit better, given what we're seeing here, just to try and get the results a little bit more optimized. But for purposes of the this tutorial, I think we'll be fine. So
can we remove some of the particles manually?
You can go through once the micrographs have been. Every time I hit Autobox, it'll undo any manual particles that you've deleted. But yes, you can manually delete particles if you don't like specific ones after you've done the autoboxing process.
Okay.
Whether it's worth going through and manually deleting all of the particles from all of the micrographs or not. I mean, projects nowadays often have 1 million particles and 5,000 frames. So you really want to have a process that's pretty much fully automatic, and just try and keep the number of particles which are bad to a minimum. If only, say 1% of the particles are bad or 2% are bad, generally the algorithms will do a good job of getting rid of those when you do the 3D reconstruction process. If you have 10 or 20% bad, then that can start having some real impacts on your final structure. However, I should also warn you that sometimes it won't make the resolution of your final structure worse. It'll just make the shape of your final structure worse. So it's possible by including bad particles to actually get structures which evaluate as having a good resolution, but not really having a good resolution. Okay, yeah, so that threshold is just way too high.
I have a question. So if the final resolution of the 3D structure is disturbed because of the bad references, how can we identify that? Like you said, sometimes it is the resolution, sometimes it's the structure. So how can we identify if the structure is disturbed because of bad references, like 10 to 20%?
So it's not bad references, it's bad particles.
Bad particle.
But
reference.
it we'll have to talk about that once we're at that stage.
Okay.
I can't explain it easily where we are right now. All right, let me. Yeah, I got a bad train this time. You
Wait.
can see that it's.
I have a question. I'm curious. In the training, does it use the metadata like the CTF parameters? And
In what sense?
does it? Are they inputs? Do they take inputs from that information? I'm just curious.
You mean is the metadata input to the network in some fashion?
Yeah, yeah.
Oh no, just the
Oh,
image.
I see. Oh, I see. Okay.
Yeah, no, the metadata has no role in the particle picking process.
Okay.
All right. So the reason I was having so much trouble was not just that there was an issue with the good versus bad. It was actually that I also needed to adjust the first threshold when I retrained the network, and I forgot to do that first. So now that I've adjusted the first threshold, I'm getting slightly better results, and you can see it's doing a pretty good job of avoiding that. But it's still probably not going to be perfect in terms of avoiding all of the contamination. Anyway, let's check a couple more images here just to make sure our threshold is kind of okay. And then I'll just go ahead and say autobox all. So when you guys did your tutorial, you would have presumably just used the already picked particle locations. In this case, I'm actually just I'll go ahead and use these particle locations that we're getting from this deep learning picker. Now you'll see particles found excluding bad particles. That's the excluding bad particles or the contamination. So this is what it's getting from the first neural network, and then this is what it's excluding based on the second network. So this will take a minute or so to get through all of the micrographs.
Actually, I have a question.
Yep.
So, can you like evaluate like the performance of the network based on the train out file? Like when you're done training a network, there's will be like two train out file being
You want to
output.
check the fidelity of the network to see if it matches the
Yes.
input training data.
Yes. So
you could do that, but we don't have a tool for doing that.
oh. Yeah, actually I kind of like confused because like I do it on my own data set. The training out set for the background versus particles kind of makes sense, but the others is always give me some weird things. So like what?
It's often hard to train that second network well to recognize things like that as being bad, because it looks so much like a particle in many ways. It's a convolutional network, so it's basically learning what particles are based on their texture, and the texture of this isn't actually so much different than the texture of a particle. So that second network is actually pretty challenging to train. I mean, if you are a deep learning programmer and you're trying to understand it from that perspective and trying to improve things, then what you're talking about makes sense, sort of looking at that network fidelity. But for a typical end user who doesn't know anything about a neural network or what a convolutional neural network is, basically just looking at the cost and making sure that it's sort of decreasing and sort of eventually kind of stabilizing a bit is all we really target.
Okay.
Okay. So we should now have. So if we look over at the left here, we should now be able. Oh, all right. It didn't update the display. Let me just. Not sure why I didn't update it. Let me just launch it again. Okay, now you can actually see how many particles it found in each image. And that's basically it. So now we have gotten to the point in the tutorial where we've basically imported the box files at this point, right? So that thing we did with the ConvNet particle picking was a replacement for this importing the known box locations. So we still need to do this next step, particles generate output, and that's basically where it just takes all those box locations and pulls them out as stacks of particle images. So we generate output. Particle size doesn't make any difference at all here. Box size is what matters here, and we want to use 256. And the default parameter should be fine. It's going to use all micrographs. It's going to write the particles to the output file. We're storing with 6 bits of precision in the raw data, and that's it. So if we look at this task manager, we can see when it finishes. We can also look down here. You can see this little warning: no angstrom per pixel specified using 1.275 from project. So we had left this as -1, and if you say -1, then it'll use the default value from the project, which is correct in this case. But this is one of the places where people sometimes get into trouble if they failed to read that line in the instructions and we didn't distribute the info project.json file. If you don't set that in the project settings correctly, then you can have the wrong angstrom per pixel value, and then all the CTF determination stuff will be messed up, and you basically have to go back to the first stage of the project. Okay, all done. Particles written to particles, blah, blah, blah. So if we open this and look in particles, we'll now see a stack file for each of the micrographs. And the number of particles here should be equivalent to what we saw in Boxer for the number of particles. We next need to make a particle set. We're going to do it for all particles. And the set name we're going to use is all, meaning that we're including everything in our set. There are strategies you can use here to deterministically exclude certain subsets of the data. So for example, if the micrograph was too far from focus, or the micrograph was too close to focus, maybe you want to exclude those. Or if you did a quality assessment on the raw micrographs, you might want to exclude particles that have a quality below some particular threshold value or something. We're not going to do any of that. We're just going to include all of the particles. Okay, that's done. That process just takes a second. And now we should see that we have a sets folder, and we have 11,656 particles. So that's a lot more than the 5,000 something that was found in the original data set. Sorry, in the box files that are provided with the tutorial, I think there's about 5,000. So we found about twice as many, even though we did it fairly conservatively. All right, so the next thing we need to do, back to the tutorial, is the CTF correction process. So this is basically, when we imported the frames, it already did an estimate of the defocus. But when it was estimating the defocus, it was estimating the defocus for the entire micrograph. That's pretty good. And in most cases, it's going to be fine, but it includes things like, if say the edge of the carbon film is included in the frame, it includes that will tend to often dominate the defocus determination. And the particles may not be sitting in exactly a plane corresponding to the middle of the thickness of the carbon film or something. Anyway, the point is the defocus value you can get for the whole frame may be off a little bit. So this gives the software an opportunity to sort of correct the defocus a little bit. And then it does the phase flipping process, which we do as a pre-processing step. It's all automatic. You just say CTF auto process. You indicate whether this is a high resolution project, a medium, so high resolution sort of better than 5 angstroms. Medium resolution, it's if you mouse over these, it'll tell you what it's for. So if you're doing like negative stain or something, you'd say low resolution. And this just produces different types of output files, which have been filtered in different ways for speed and convenience. All of the other options, the defaults should be fine, although I'll change threads back to 8 again here. Sometimes setting const b factor, it doesn't really do much of anything, but if we set it here, then the parameters, if we try to visualize things later, will look more self-consistent. In other words, changing this, leaving this as -1 won't do any harm in our final reconstruction. It's just visualization in the intermediate steps where it's convenient to have a constant value. Defocus range is fine again, and it will use the current defocus that it got for the whole frame as sort of a starting point. So it'll only sort of tweak it a little bit around that point. And I think that's it. Let's take a look and see if there's anything else. There's a lot of explanations there, some of what I just said. Yeah, there we go. Auto process. Okay, that should be fine. Yeah, it suggested 80. I put 100. Doesn't really matter. Threads. Yeah, that's it. Nothing else changed. So we launched that. So we can actually see the percentage completion on this as it runs, although it's very coarse. So this process actually runs in several steps. First, it determines the defocus parameters, and then it sequentially generates each type of output file for all of the input files. When it talks about skipping bad particles, the bad particles it's talking about here are particles that were boxed out too close to the edge of the frame. So it included a bunch of just flat zero density outside the edge of the micrograph. So those automatically get excluded at this point in the process. Okay. So the first step is it determines the correct CTF parameters for the particles from each frame. Then it determines an estimated structure factor for the one-dimensional structure factor for the particles. Then it goes back and it does sort of refits the data quickly just to make sure everything's nice once it has the structure factor. So it uses the structure factor as a tool to tweak the defocuses a little bit more. And once it determines the defocus, the CTF parameters again, then it'll start the output generation process. Won't take too long. So we're getting close to the end of an hour here. I'll go a little bit over an hour. Hopefully everyone can stay at least a little bit, because I want to at least kind of get through the making the 2D class averages step today. Anyone have any questions about any of this while we're waiting? Or have any problems when they did any of this?
So when doing the correction now, is it estimating the defocus landscape per particle? So does it divide it into patches, or are you still limited to the whole micrograph?
This is just determining the defocus on a whole micrograph basis, but it's using the particles to determine the defocus rather than regions of the entire micrograph.
Okay, understood.
Yeah. So it's determining basically the mean defocus of all the particles in one frame.
Okay, great.
While this is running, we can actually open the visual CTF really quickly and take a look at that. We just open that with the default parameters. Yeah, so now we could take a look at, let's see. So we have a control panel here, which shows us each of the micrographs. Here we can see the 2D power spectrum. Here we can see the 1D power spectrum. I'm zooming in with the right mouse button here. So the black line represents the raw power spectrum computed from the particles themselves. You'll notice that it has features here. If you do a whole micrograph CTF estimate, you actually won't see a lot of these features you typically won't see. That's because this was computed from the particles. So what we're looking at here is the contrast transfer function multiplied by the structure factor of the particle. So these features you're seeing here at low resolution are coming from the shape of the particle averaged over all its different orientations. The blue curve is the estimated, is the fit curve, basically, which has also been multiplied by our structure factor estimate. Now you'll notice that there's a gap here, and that gap is basically because of the B factor adjustment. So if we adjust the B factor, we can get that to match pretty well. but then we'll find that the peak amplitude doesn't match very well at high resolution. So this sort of B factor approximation that we use, that the envelope function of the microscope should look like a Gaussian fall off, isn't completely accurate. There are other components of that envelope function which are non-Gaussian, but again, it doesn't hurt anything in the reconstruction. It's really just used when you're kind of doing this visualization. So what I'm saying is it's fine if there's a gap here. The key point is that all of these CTF oscillations should match out at as high resolution as possible. So these are sorted in order of defocus. So this is the closest defocus image, and you can see that image is kind of terrible anyway. I think that's the one I left 1 or 2 bad images in the data set just for the heck of it. So if we scroll through this, we should see that it's getting farther and further from focus as I move down through the set, but that it fits pretty nicely for all of the different curves. Anyway, so that's the results of all the automatic CTF processing there. So it's almost done now. It's in the generating the last set of processed phase flipped filtered particles. So if I open the browser again here and look under particles, now we'll see that for each frame, so this is 21, for example, is one of the frame numbers, micrograph numbers. We now have the original particles. We also have the CTF flipped particles at full resolution, the CTF flipped particles low pass filtered to 12 angstroms, and the CTF filtered particles low pass filtered to 5 angstroms. That's what these 12 and 5 are what you get when you ask for high resolution refinement. And the idea is that the original box size is 256 by 256. The LP12 particles are only 84 by 84, which means the processing should run something like 20 or 25 times faster. So by doing your preliminary processing, like making your initial models and doing 2D class averaging and stuff like that on these low pass filtered particles, you can save yourself a lot of computational time. So it'll go ahead and make sets for you for each of these different types of particles, and then you can use them for whatever purposes you want. If you want, you can actually use the full resolution particles for everything. You don't have to use any of the filtered particles ever at all. It's just that some of the jobs that you run will take longer to run than they need to achieve whatever aims you're after. Okay, that's almost done now. It's in this last stage where it's computing invariance. 121. I'm just looking to see how close it is to being done. All right, so we can get set up for our next job. I just won't launch it immediately. So the next thing we're going to do is this bispectrum based class averaging. So there are 2 algorithms here. This actually dates to the original version of EMAN2, 20 years ago, where it does an iterative process to make class averages. It's fairly time consuming. It's still a lot faster than Reliance 2D analysis, but it's somewhat time consuming because it's iterative and that sort of thing. This new method is based on bispectrum analysis. It uses invariance for each particle to classify the particles together in one step, and it can produce class averages extremely quickly. And for most projects, this will produce results that are as good or better than the results that you get using this. There are some projects you may find where this actually still works better. So I would always suggest trying this. And if you don't get set class averages that are what you expect and they don't look very good, then you could go ahead and try this one instead. But this one works fine for pretty much every case. Now, the other thing you have to do is there's 2 different reasons why you might make class averages. One reason is you want to get you want to get some less noisy views of particles in a range of different orientations that you can use to make an initial model. For that purpose, there's no reason you need to use all of the data. You could just process, data from 5 or 10 micrographs at low resolution, and that'll give you enough different class averages that you can make your initial model very easily. Another thing you can do with this is actually try and identify bad particles. So if you're left with some ice contamination particles or something like that, you can use this step to help eliminate some of those. If you do that, then you have to use all of the data. Otherwise, you won't be able to eliminate the bad particles from the sets of the data, the subset of the data that you didn't run it on. So we're going to go ahead, and that's what the tutorial has you do, is generating these reference-free unsupervised class averages, and we're going to do it on all of the particles. And then that would allow us to take this next step of eliminating some of the bad particles at this stage. Again, this is an optional thing. There are other ways of getting rid of bad particles later in the processing, but this isn't a terrible thing to do if you think you might have some ice contamination or something in your data. It'll save you from certain problems that you might run into later. Right. So I'm going to go ahead and I'm going to tweak the parameters a little bit. I'm going to say 128 classes. And we'll tell it to use 8 threads instead of 4 threads. And pretty much we shouldn't really need to change any of the other options. The defaults are pretty good for just about everything. I don't think I can take a look at the tutorial and see to change anything else. Number of classes, number of basis footprints. Well, that's interesting. I'm not sure why it uses such a big number. All right, well, we'll go ahead and put 24 in there. I'm not going to explain right at this moment what that means, but let's see, rotate, translate, tree. That's the default. That's what we just did. Class averagers, CTF weight, auto-filled. Interesting. That's probably the default. Yeah, that's also the default. Right. So everything is basically the default. So the only thing we need to do now is specify the input file. It looks like, yes, it finished running. So I should now be able to browse and look in sets. And now you can see in sets, in addition to the all that we had before, we now also have the all full res, LP12, LP5, and then this file contains the invariants. And you can see the number of particles is the same in each of these. So I'm going to go ahead and run this on the, we're not going to wait for this today anyway. I think it won't take a long time to run, but it's still going to take, probably 10, 15 minutes or something. And we were already over an hour. So I'll go ahead and run it on the full resolution data. Just so we'll see the bigger particles, because I don't care if it takes a little bit longer to run right now. And then we'll look at some of those results next time. All right, so we'll get that launched. And you can see building initial averages. And we'll start seeing it do things in a second. Yeah, there we go. So it's already finished classifying all the particles, and now it started making class averages. The class averages are what will take longer to run. The first step of the process doesn't matter whether you use the downsampled particles or the full size particles. The class averaging is what will take longer. If we browse here, we can see we have a new folder now, R2DB00, and it's started building up classes in here already. So we've got 8 already. So we can see some of these. So you can see those are nice higher contrast views of different views of the particle. Anyway, that'll keep running for the next 10 minutes or so. It's going pretty fast, so it may not take as long as I thought. Oh, it's up to 30 already. Yeah, anyway, that's fine. We've already gone over an hour today. Any other questions today? I know we certainly didn't get through the full process this time, but yeah, we got pretty far. Okay.
I had some questions regarding the 3D refinement stage, but
yeah, we'll talk about that when we do the 3D refinement next week.
Okay.
Yeah, I realize it's going to take more than a week, 1 hour basically, to get through each of these stages because there's so much involved.
All right.
I think next week we should pretty easily be able. I mean, we've got the class averages. Making the initial model shouldn't take very long at all. So I'll go ahead and run this on my machine. We'll at least have a reference run on my machine that we can look at, so we won't have to wait for the refinement runs to run during the 1 hour period next time. So I think we'll finish off the single particle analysis in the next meeting, and then the meeting after that we'll do the subtomogram average.